Yeah, my name is Andreas Stark. I'm a team lead for embedded software development, specifically for the ground support systems and all our test stands at our Rocket Factory Augsburg. Also in my team, we do mission control center, data logging, user interfaces, everything that is necessary to get the rocket to launch and then hopefully to space from there. Yeah, can you see my screen?
We can see you right now at the moment.
Okay, perfect. So yeah, today I'm going to talk about the next generation launch vehicles and how we can leverage this new opportunities to bring down the cost of access to space. Yeah, so welcome everybody. Yeah, I'm Andreas Stark again, team lead. I've been at Rocket Factory for a little bit longer than 1.5 years now. As you know, Rocket Factory is a fairly young company, started in 2018, but growing quite quickly. And I will guide you a little bit through what we are developing, when it will be ready, and hopefully, and why our approach will lower the cost of access to space. So first of all, our vision at Rocket Factory is making space accessible for every business model. So by bringing down the cost of access to space, just the entry hurdle into space will be a lot lower in the future, and this will enable many business models in space, because just like the cost of getting something to space will be much cheaper. As we all know, new space here, so satellite-based real-time data offers great opportunities, and so also the demand to get it and provide it is large. So how are we going to achieve that? So our mission is to build rockets just like cars. So our goal is not just to build one rocket. The goal is by the end of the decade to have around 50 launches per year, so roughly one launch per week at multiple launch sites around the world, and try to get there by strictly being cost focused, using as many as possible commercial off-the-shelf components, standardized components that we can just reuse from other industries, for example, from the automotive industry, to build a very reliable yet cheap launch system. So, as you know, there's the value chain in space. It starts with satellite customers. They want to launch satellites to space to offer their value-added services. Once they decided and have a business model around it, the satellite is manufactured. I think all that is pretty well and efficient nowadays. But then there's this big hurdle of getting your satellite into space and not blowing the budget on doing that. So launch and then also in-orbit services, quite expensive, at least for most parts of access to space. And then the last part is, once the satellite is up there, you can operate it and satellite operations, but this is also fairly well figured out. So the highest cost bottleneck, in our opinion, is the launch and in-orbit services. And so by offering micro launch services and payload deployment, we try to address this. Sorry, just one question. So do you also see this title bar, or is it only on my screen?
Well, the presentation is well visible.
Okay, so you don't see the navigation bar?
No.
Okay, perfect. All right, so then, like most of the business models in space are centered around either observing Earth or providing connectivity from space. So in the observing Earth bucket is mapping, support for agriculture and farming, figuring out where to provide and deploy fertilizers, how crops are going, how the landscape is, water, and all these things. Infrastructure monitoring, as you've just seen in this presentation before, logistics and mobility, planning better routes, maybe for ships, and remote sensing, so having sensors in space in remote areas where it's hard to deploy ground-based sensor networks. And then the other bucket is connectivity from space, Internet of Things, broadband, narrowband, cloud computing, and all that. And as you know, all of these business models require larger or smaller constellations, but yeah, only a small number of business models gets away with just having a few large satellites in space. So it's really building a constellation with multiple satellites is key for this market. All right, so how are we trying to do that? First of all, superior technology. As you know, the heart of each rocket or its DNA is a propulsion system. So the more efficient the propulsion system is, the cheaper the access to space is. Basically, the more payload per launch mass you can get to space, and it just bring down costs significantly. Then the next thing is you cannot start with a system and then try to make it cheap. It needs to be designed from ground up to be cost efficient by using the right products, the right processes to get there. So from the beginning, a company needs to focus on industrializing rocket production, focusing on low cost and reusability. Basically, once you ran through a couple of billion building your launcher, then it's really hard to find an affordable business model to provide access to space. So we do that by using as much as possible industrial parts, very efficient production technologies, additive manufacturing, and so on, to create those cost advantages. And then the last piece is the last mile delivery, having a specialized orbital transfer vehicle or third stage that can not just deploy a satellite, but also provide in-orbit services and also remain in space for a longer period. So to go a little bit more into details on how that looks in reality, as I said, the efficiency of the propulsion system is key. So we are targeting a propulsion system that is a oxidizer-rich stage combustion engine, so a fairly efficient method of propulsion. I'll dive into that a little bit later as well. Around 100 kilonewtons of thrust, with the currently the focus of lifting up to 1.3 tons to a polar orbit, using this 9-engine cluster in the first stage, and then the same engine just modified as a vacuum engine in the second stage as well. I don't know how familiar you are with rocket propulsion. I was not very much, as I'm coming from the software world, but so yeah, stick with me for a little introduction. So the very common system in propulsion is an open cycle rocket engine system. So the way this works, you have fuel and an oxidizer. So this can be, for example, liquid oxygen and RP1 rocket propellant, or obviously liquid oxygen, liquid hydrogen, and so on. So then the fuel and the oxidizer somehow needs to get to the engine, to the combustion chamber where it's ignited, and does a chemical reaction, burning, exploding, however you name it, to create a fast stream of particles out of this engine that creates this thrust, pushing then the rocket forward. So there's multiple ways of getting these two components into the engine, but a very common way is using turbo pumps. Somehow this turbo pump needs to be powered, so this can be either electrically or by some other means. So the very common approach is using a gas generator, pretty much like a turbocharger in a car, just a little more advanced, where fuel and oxidizer are burned in a small chamber, creating thrust to spin this turbine wheel. This one spins these two turbo pumps, and then they pump the fuel and oxidizer into the engine, and creating the material, bringing the material for the combustion. The downside of using this is you're wasting quite some of your propellant just to spin the pump, and it's not used for propulsion. So as you're wasting stuff and using not for propulsion, your efficiency goes down. So one approach of mitigating that and increasing your efficiency is basically having the same principle as before, but instead taking the exhaust or the mildly burned either fuel or oxidizer from this turbine wheel that spins the turbo pumps and feeding that back into the combustion chamber to also contribute to your overall propulsion and thrust. And so this is what we do. There's two different ways: oxidizer rich and fuel rich. Oxidizer rich means we pump all our oxidizers, so all the liquid oxygen we're using through this turbine wheel, and only a small amount of the fuel, so that we just get so only a small fraction of the oxidizer burns and spins this turbine wheel. And so then basically the heated up oxidizer with a little bit of the burned fuel and all the fuel meet here in the combustion chamber and then propel the rocket. So this leads to a roughly 7% increase in fuel efficiency. But as you know, if you're more efficient, then you need to carry less fuel. And if you need to carry less fuel, you need to burn less and so on. And so overall, this results into a 30% increase in payload capabilities, which is quite significant. Also, since everything goes through this very hot combustion chamber, it's a very clean burn, and you don't get the sooty exhausts like you get otherwise. All right, so as I said, the propulsion system is the DNA of the rocket. So we had an online challenge, and many contributors, I think more than 2,500 people voted and contributed name suggestions for our engine. In the end, it was selected the Helix engine because it's the DNA of the rocket. Yeah, we say it's an automotive grade rocket engine. Yeah, think of it more as like a Formula One automobile and not like the regular street car. But still trying to get really a production set up where we can have a serial production as you would do for Formula One engines. Yeah, some details of our engine that we already hot fired a couple of times successfully, and also for some longer durations. As you can see, the fuel goes in, the oxidizer goes in. Then we have this pre-burner, as you said, you just saw, that generates a stream to power the turbo pumps. Here you can see the turbo pumps, the LOX pump and the fuel pump. They are spun by this gas stream from the pre-burner. And then in the beginning, you need to get the system going. There's a spin start system where you pump some gas through, so it starts spinning and you get your initial fuel to start the combustion and ignition in the pre-burner, and then pumping all the fuel and oxidizer into the main combustion chamber. Also, from the beginning, this engine is designed to be maintainable and reusable. So really, the goal is to have it easily maintainable and refurbishable, and should be able to be done by a technician in a couple of hours. So one thing is the turbo pump is designed to survive up to 20 flights. And then the thrust chamber up to 4 flights currently. And then it's reignitable. This is particularly important for the upper stages. So we're using an igniter called TTAP. It's a pyrophoric substance, so once it comes in contact with air or liquid oxygen, it starts burning and hence igniting the engine. All right, how do we test this this engine, and how do we make sure it performs as expected? And since I'm, as Martin has introduced me, the team lead for doing all the test stands and test and control systems, this is our current engine and second stage integrated stage testing test stand. It's located in Kiruna, Sweden, so at the Arctic Circle, very remote. But yeah, we can leverage the nice infrastructure that's there from the mining and also from the SSC that has its headquarters there. And as you can see, we have our main test stand here. We call it vertical test stand. Right here with this housing. So in the winter at -30 or -40 Celsius, people can still work at the engines while heating this housing up. It has two positions, an engine position and then an IST position in the back. So we can pretty quickly interchange between the two tests. And then at the side, we also have a second smaller test stand. They call it the horizontal test stand for power pack turbo pump testing, for example. And then you see the site layout is some storage of fluids and propellant and some workshop and offices. Sometimes you get some reindeer visitors or foxes as well. A couple of weeks there was a little baby reindeer close to the site. Obviously, we make sure before we do some hot fires that it's all clean. So yeah, this is the vertical test stand. Is that two test positions for the helix testing and stage 2 testing. Yeah, in a nice snow winter wonderland currently, and hopefully soon in a more human-friendly summer in Sweden. And then the horizontal test stand for power, we call it the power pack. So the power pack is a pre-burner and the turbo pump to do optimizations and many tests there. And this is the second test stand that we utilize here as well. All right, so now let me show you a little video of our hot fires.
Five, 4, 3, 2, 1. Ignition.
As you can see, we routed our turbo pump roughly at 30,000 RPM. Right, yeah, quite impressive if these 100 kilonewton engine ignites and shakes everything up. Okay, so then the second key aspect of bringing down the cost of space is the vehicle itself. So for our stage structures, we are using a common tank design for both stages made of stainless steel. It's fairly cheap. Also, steel has the advantage of being reworkable and very reusable after coming back to Earth from space. And also we do some obviously tank testing. So quick video from a burst test that we did here in Augsburg in Germany. Sometimes it's really important to go over the limits to know where your limits are, and this was exactly what happened here. Going over the burst pressure of the tank to see where it really is. All right, and then this third aspect is this orbital stage, which is an orbital transfer vehicle that can also fly missions in space and stay there for longer times, deploy satellites at various times at various positions, for example. And we use that to have dedicated and rideshare missions. And then, going really to operate in the future, in the next couple of years, as a taxi fleet that is continuously launching and being repaired and upgraded. The first stage is really the cost driver. Half of the cost is the first stage. Also, really production capabilities are a problem once you target 50 launches per year, because you need to build 50 times 9 engines then. And so it's really, if you cannot reuse, you're really in a bad spot, and you need to try to manufacture all of that, which is a challenge by itself. All right, so general, where are we company-wise? Started in 2018, then built turbo pump, prototype of the second stage, test fire the orbital stage, build the test site in Sweden up, as that you saw, moved to a new facility to enable the growth of the company, doing a main engine test campaign, building the tank demonstrator and doing the burst test, and then in April doing really the flight configuration of the Helix engine and doing that long duration hot fire campaign. And then 2023 should be a very exciting year, and targeting liftoff by the end of the year. Where are we currently? So this was our second stage for the integrated stage test, ready to go to Sweden. It's already there on the test stand. On the test site, as you can see, it was lifted in there in the crane. It's being tested currently right there. And then also our launch site on the Shetland Islands is also coming together quite nicely. So just before Christmas, we erected the launch stool. And then the next steps are erecting the umbilical tower and the rest of the infrastructure, so that we are ready to do the stage 1 integrated testing campaign, and then also stack tests and launch. A little bit about RFA. We have a quite large facility, including clean rooms, a large office, a good supplier network in southern Germany, where much of aerospace and automotive industry is located. And also we are building up our automotive scale industrialization, focusing on the serial production, as you can see, additive manufacturing, metal 3D printing, and all that streamlining there. And a quite fast-growing company. Now we are at 220 full-time employees from over 30 nations. So it's a quite interesting and a nice work atmosphere, working with all these diverse people from around the world. Also, we have obviously a lot of experienced people in key positions that bring a lot of industry experience, coming from, for example, from Rocket Lab, Blue Origin, the ESA, and so on. And with that, thank you for again for listening in. Hope to you follow us on our social media and follow our campaigns. We quite frequently publish material on and updates on where we are and how it's going. And obviously, also we are looking for smart engineers. If you're interested, always a good opportunity to knock at our door. And then opening it up for questions.
Perfect. Well, thank you, Andreas. That was very insightful, and congratulations on all the success that your company has been seeing. And obviously, I personally has been exposed to your company for quite a few years right now, and even know some of the teammates as we've been having these discussions privately. So, as European soil haven't seen the launch yet, it's really exciting to see and follow the journey of RFA, and fingers crossed. And I'm sure you're going to be one of those companies that and the frontier of European space market, or globally, preferably as well. So, I have a couple of questions here from my side. So one of the questions is, what are some of the key technical innovations that are driving development of next generation launch vehicles, and how might these innovations be applied to other areas of the space industry, such as satellite manufacturing and in-orbit service?
Yeah, I mean, I think one of the really the key aspects is using additive manufacturing. I mean, many companies use it nowadays because it just, I mean, using a 3D printer to produce not just plastic, but also metal parts is just like a game changer, because you can iterate design so much faster. That is the one aspect. So basically we can do a test on an engine. We see something is failing or not behaving as expected. We can, you know, iterate the design in a matter of days, and then we can print out a new part, obviously based on 3D printer availabilities and so on. But the turnaround time and design iterations is way shorter than it used to be. Also, since we are doing that in-house and we're trying to bundle the key areas of prototyping in-house, so that we don't need to wait and be in queue at some supplier for these core parts, for at least until the design is proven and stable, is one of the game changers. The other one is really, I think, starting small, very focused, learning from the others, but then also building it up with the bare minimum, shooting for what you really need, leaving away all the nice to haves for a minimum viable product for your first product. I think that's also a key enabler, and it really speeds up things. And obviously it's also challenging to work in such an environment where you really need to think about, is this really necessary? What is really needed to get to space and to provide a service, and what is nice to have, and which one can I leave away, just to provide this really very focused product. That's the other thing. Obviously on the software side, there's also many things. So if you have a powerful software team in-house that can do many and address all the control challenges that you're facing, both on the rocket and on the ground, that's also a key benefit, because sometimes you have 2 years of requirements writing for a project, and then you can hand it over to a supplier, and then he builds some software and comes back a couple of years later, and then it's not the exact same thing that you actually need, or your design evolved. So having these really like close tie-in between mechanical design and also control software, and then the combination also with tying in the test team, right? So that really you can have really short design iteration. I think that's really key in figuring it out and making a design stable and proven for space. Yeah.
Perfect. Well, thank you for that answer too. So for the people here who are going to be submitting questions after the session, you can also submit those questions here in a Q&A chat for Andreas that could be sent later, or you can simply find him on the speaker list, where you can set up a private meeting. You're going to find his contact details, his company details of RFA, his personal LinkedIn. So feel free to reach out and browse through that list. Also, of Andreas yourself, you're gonna find these people. They're gonna be speaking here for networking purposes too. But I greatly appreciate the time. Once again, it's good to see that the company's growth. We're pulling here for the company for sure, cheering the company on. And thanks for your time, and we hope to see you next year, and hopefully you're going to be sharing more of these success stories with us too. So
yeah, thanks again for having me, and thanks for your best wishes. We can really need it. I mean, it's always a nerve-wracking to watch one of those larger tests ongoing, as you can imagine, and the launch. And so yeah, thanks for that. It's going to be an exciting year. As like next up we will have stage 2 hot firing, then stage 1 drain testing, stage 1 integrated testing, and so on. So many tests, and then stacking the rocket up and trying to launch. So yeah,
right.
Thanks a lot for
Godspeed
this.
with that. So thank you again, Andreas.
All right.
Appreciate it.
Thank you very much. Take care.